We are going to talk about the second kind of transformation that we're going to do with functions, which is reflections. And if you'll remember from geometry, this is another kind of rigid transformation, right? We can do a rigid transformation. So this is a rigid transformation, and there's two ways we can reflect things. We can have a vertical reflection or a horizontal reflection. So a vertical reflection is a reflection across the x-axis, right? From below the x-axis to above the x-axis. So an example, if in this graph, our blue function is our original function, and this green function is our vertical reflection. And the way that happens with the equations is it becomes negative of the original function. And you can see why that would happen. If we had an x value, right, and then if f of x gave us, our original function gave us some value up here above the x-axis, say, then negative f of x would give us the negative y value as an output for that x value input, right? So negative f of x gives us a reflection about the vertical axis, a vertical reflection about the x-axis, sorry. Okay, we can also do a horizontal reflection about the y-axis, okay? So here's our original function is blue. A horizontal reflection is across the y-axis. It's this new red function, red graph, right? A horizontal reflection. So everything that was on the right side moves to the left. Okay, and the way that happens is g of x becomes f of negative x, right? So if we had some x value here and it gave us an output value there, to get that same output value, we take negative x along the x-axis, right? So f of x gives us that output. F of negative x gives us that same output. Okay, so a vertical reflection, the minus sign is outside the function. For a horizontal reflection, the minus sign is inside the reflection. So here's an example. We have the square root function, and if we have a vertical reflection, right, it used to be above the x-axis and now it's below. So we would write that as minus square root of t, right? The minus sign is outside of the original function. That's a vertical reflection. But if we did a horizontal reflection and reflected it across the y-axis, we'd have h of t, our new function, would be the square root of minus t, where the negative sign goes inside of the original function. What if we have a table? Okay, we have input values for x, 2, 4, 6, 8, and some output values, f of x, right? What if we wanted to make a table for g of x, which is minus f of x? Well, our input values would stay the same, and our output values would just be the negative of our original function, right? So minus 1, minus 3, minus 7, minus 11. The numbers are all the same, they're just minus. What if we had h of x, which would be a horizontal reflection? It's f of negative x. In that case, our output values stay the same, and our original input values all become negative. Okay, so let's look at this equation, look at a word problem here. So a common model for learning has an equation similar to this one. K of t is minus 2 to the negative t plus 1, where K is a percentage of mastery that can be achieved after t practice sessions. So this is a transformation of this original toolkit function, right? This is an exponential equation. Our base is 2, our variable t is in the exponent. So this is a graph of our original equation, 2 to the t, right? But we want to graph this one. So there's a bunch of transformations happening there. Why don't you think for just a minute which transformations are happening? Well, we have a horizontal reflection, right? This minus t up here in the exponent is a horizontal reflection. We also have a vertical reflection because it's a minus 2 to the negative t, right? We've got that minus sign there. And we have this plus 1 added on the end. That is a vertical shift, okay? So how are we going to graph this? Here are 3 things. We've got horizontal reflection, vertical reflection, and vertical shift, okay? Something that's very important is you must do the reflections first and then do your shifts, vertical or horizontal shifts last, okay? So first, let's do a horizontal reflection, right? Our original function looked like that. It was going up to the right. We do a horizontal reflection, and it goes up to the left, right? It reflected about the x-axis. And we can see our original function crosses the x-axis, the y-axis at 1, right? That's our base function, an exponential, crosses the y-axis at 1. So first we did a horizontal reflection, then we're going to reflect this vertically, right? And lastly, we're going to shift it vertically up, right? So vertical shift up, the place that is crossing the y-axis, our y-intercept, used to be -1, right? And so it shifts up 1 to become 0, the origin. Okay, so we did first a horizontal reflection, then a vertical reflection, then a vertical shift. Okay, let's talk about even and odd functions. And to do that, let's first look at this equation x cubed. Okay, so here's just a toolkit function x cubed. Let's look at the horizontal reflection of that, f of -x. If we reflect that across the y-axis, here we go. This is our horizontal reflection of x cubed. And then what if we reflect it again, did a vertical reflection of this function? What do you notice? We get the exact same function, right? There's a special word for that, okay? That is called origin symmetry, okay? If you can do a horizontal reflection and then a vertical reflection and get your same function back out, that is called origin symmetry. And those are very few functions that have that property, but they have a special name. We call them odd functions, okay? So there's even and odd functions. Here's the official definition. A function is even if for every input, f of x equals f of -x. Well, let's think about what that means. This looks familiar. This looks like a horizontal reflection, right? So this is saying the function equals its horizontal reflection. What would that mean? That means it's symmetric, right? If you fold the function in half across the y-axis, it will match up. That is an even function. A function is odd if f of x equals negative f of -x. So that means just what we talked about with x cubed. If you do a horizontal reflection and then a vertical reflection, you get the same function back out. Okay, so this definition, so if you have a graph, you can look at the graph and see if it has symmetry, if it has y-axis symmetry or origin symmetry. If you just have an equation, this is how you determine it. You plug in f of -x, right? If f of x equals f of -x, or if f of x equals negative f of -x, here it's odd, here it's even, okay? So let's do an example of testing if something is even or odd. So they give us this function, f of x equals x cubed plus 2 to the x. So let's find what f of -x is. F of -x, let's see, everywhere there's an x, we're going to put a -x plus 2 to the -x. And let's simplify. -x cubed is just -x cubed. And here we get minus 2x. Let's see, we could factor out a minus and get x cubed plus 2x. Oh, and look, that is our original function. So this is minus f of x. So f of minus x equals negative f of x, or we could write that using the definition they give us, f of x equals negative f of -x, right? And that should look familiar. That means that this is an odd function. And it has origin symmetry. Okay? So it's a pretty easy test to plug in a -x into your original equation and see if it turns out to be even, odd, or neither. Many equations will be neither. Here is a trick. You might know this. If all of the exponents in a polynomial are odd, the function is odd. If all of the exponents in a polynomial are even, it's even. And if it's a mix, it's neither. Okay, so that's a little shortcut, but it's important to know how to actually plug it in and test it that way. Okay, so that's reflection symmetry and also even and odd functions.